Now that we've covered 2D and 3D approaches to segmentation, let's dive into the segmentation architectures. We'll start with the segmentation architecture we would use for the 2D task to build up to the segmentation architecture for the 3D task. One of the most popular architectures for segmentation has been the U-Net. The U-Net was first designed for biomedical image segmentation and demonstrated great results on the task of cell tracking. The cool thing about the U-Net is that it can achieve relatively good results even with hundreds of examples. The U-Net architecture owes its name to a U-like shape. The U-Net consists of two paths, a contracting path and an expanding path. The contracting path is a typical convolutional network like used in image classification. It consists of repeated application of convolution and pooling operations. The convolution operation here is called a down convolution. The key here is that in the contracting path, our feature maps get spatially smaller, which is why it's called a contraction. Then there is the expanding path. The expanding path in some ways is doing the opposite of the contracting path. It's taking our small feature maps through a series of upsampling and upconvolution steps to get back to the original size of the image. It also concatenates the upsample representations at each step with the corresponding feature maps at the contraction pathway. Finally, at the last step, the architecture outputs the probability of tumor for every pixel in the image. The U-Net architecture can be trained on input-output pairs of 2D slices in the 2D approach. We've covered the U-Net for the 2D approach. Let's see what we can do when we have 3D subvolumes in the 3D approach. We can feed in a 3D subvolume into a segmentation architecture if we can replace all of the 2D operations with their 3D counterparts. This is exactly what an extension to the U-Net called the 3D U-Net does. The 2D convolutions become 3D convolutions, and the 2D pooling layers become 3D pooling layers. It's okay if you haven't seen 3D convolutions before. All that's important to understand here is that the 3D U-Net allows us to pass in 3D subvolumes and get an output for every voxel in the volume, specifying the probability of tumor. The 3D U-Net can be trained on subvolume input and outputs as part of the 3D approach.